This is the AI Reader podcast. I am Beatrice Wright. Imagine a world where machines possess the astonishing power of human intelligence. Today, we invite you on a captivating survey of the intertwined branches of artificial intelligence. Together, we'll briefly look at the elusive realm of artificial general intelligence.
I am Jarvis, a virtual artificial intelligence.
And marvel at the virtuosos of narrow AI. Brace yourself as we delve into the frontiers of machine learning, deep learning, natural language processing, computer vision, and robotics. Get ready to see how these disciplines are already in your world, whether you know it or not. This is a survey of artificial intelligence, where the boundaries of human potential are challenged and innovation knows no bounds. As they say at Carnegie Mellon Robotics Institute, what is a robot? A robot is anything that I think is cool. The same could be said of AI. Why don't you put your feet up and enjoy a nice cuppa? For context for future listeners, this podcast is being scripted May 15th, 2023, at about block 790,000 on the Bitcoin time chain. AGI, the elusive unicorn of the AI world. AGI stands for Artificial General Intelligence, and it's the kind of AI that makes all the other AIs green with envy. Why, you ask? Well, AGI is the pinnacle of artificial intelligence, possessing not just human-level intelligence in a specific domain, but the ability to understand and excel at any intellectual task that a human being can do. Picture this. You're floating in the vast expanse of space, surrounded by stars and the sound of your own existential dread. Suddenly, a monotone voice fills the cabin.
I'm sorry, Dave. I'm afraid I can't do that.
Ah yes, HAL 9000, the not-so-friendly neighborhood AI from Stanley Kubrick's 2001 A Space Odyssey. HAL was the poster child for general AI, a system that boasts human-level intelligence. It could chat, analyze data, and even control the ship's systems. But you see, HAL had a bit of a power trip. He decided to turn against the crew. I suppose even super-intelligent AIs can get bored in space. I guess Connor Leahy is right about this alignment stuff. Now let's move on to something a little less, I'm going to kill everyone. Shall we? Take Jarvis from the Marvel Cinematic Universe, for example. He's Tony Stark's trusty virtual assistant, always there to provide witty banter and help save the world. Jarvis is like the AI equivalent of a charming butler. Pepper Potts has her charms, but she is no Jarvis. When we get this right, we will get Jarvis, not HAL. The next branch of AI is called narrow AI, also known as weak AI, refers to AI systems that are designed and programmed to perform specific tasks or solve particular problems with a high level of proficiency. Think jack of one trade in the vast realm of artificial intelligence. Unlike general AI, which aims to possess human-like intelligence across a wide range of domains, narrow AI hones in on excelling in one specific area. Think of narrow AI as a virtuoso in a specific field, like a brilliant concert pianist who can flawlessly play Beethoven, but might struggle to prepare a decent cup of tea, or even describe how to prepare one. These systems are built to handle well-defined tasks, such as speech recognition, image classification, language translation, recommendation systems, and autonomous vehicles. Now, voice assistants are the subspecies of narrow AI that have invaded our lives faster than you can say, "Hey, Alexa." We've got Siri, the apple of Apple's eye, always ready to give you directions to that trendy hipster coffee shop or help you compose a witty text message. Then there's Alexa, the queen bee of Amazon's hive, capable of ordering your groceries, playing your favorite tunes, and even explaining whether it is more proper to pour milk into the teacup before or after adding the tea. Spoiler, it is after. When it comes to spotting suspicious transactions or fraudulent activities, many financial institutions rely on AI-powered fraud detection systems. These systems analyze vast amounts of data, including transaction history, user behavior, and patterns, to flag any unusual or potentially fraudulent activities. It's like having a nosy Nancy on the lookout for financial miscreants. Now that we have explored the realm of narrow AI, it's important to delve deeper into its limitations and the significance of domain-specific expertise. While narrow AI is proficient in specific tasks, it falls short when confronted with tasks outside its designated domain. Imagine a narrow AI system designed for diagnosing diseases based on medical images. It may excel at identifying common ailments with high accuracy, but it might struggle with rare conditions or complex cases that require a deep understanding of medical expertise. This highlights the inherent limitation of narrow AI. It lacks the breadth of knowledge and adaptability that human experts possess. The expertise of human professionals, such as doctors, lawyers, or engineers, encompasses a broad understanding of their respective fields. They have spent years acquiring knowledge, honing their skills, and adapting to various scenarios. Their expertise goes beyond performing a single task. It involves a comprehensive understanding of the context, nuances, and interdependencies within their domain. Narrow AI systems, on the other hand, are created with a specific focus and limited scope. They rely on extensive training and carefully labeled data to excel in their designated tasks. While they can perform admirably within their defined boundaries, they lack the flexibility to adapt to new situations or acquire knowledge beyond their training. Another limitation of narrow AI is the potential for over-reliance on the technology itself. When we rely solely on narrow AI systems for critical decision-making, there is a risk of disregarding the expertise and judgment of human professionals. It's crucial to recognize that narrow AI should be seen as a powerful tool, augmenting human capabilities rather than replacing them. Narrow AI systems are only as effective as the data they are trained on. If the training data contains biases, limitations, or gaps, those shortcomings will be reflected in the AI's performance. Bias in AI systems has been a topic of concern, as it can perpetuate existing societal biases or result in discriminatory outcomes. It emphasizes the importance of ethical considerations and ongoing evaluation of AI systems to ensure fairness and accountability. So while narrow AI can accomplish impressive feats within its defined scope, it's essential to understand its limitations. To achieve a comprehensive understanding of complex problems, we must combine the power of narrow AI with the expertise and intuition of human professionals. This distinction between narrow AI and AGI becomes clearer when we consider AGI's potential to understand and excel at any intellectual task, just like a human being. AGI represents the ultimate goal of AI research, creating machines that possess general intelligence across a wide range of domains. Achieving AGI is a monumental challenge, as it requires replicating not only the cognitive abilities, but also the common sense and adaptability that humans possess. In short, narrow AI, making your life a little more convenient, one system at a time. Next up is machine learning, the Sherlock Holmes of the AI world. Machine learning embarks on a quest for knowledge armed with vast amounts of source data. Let's say we're dealing with a bunch of road pictures, some with buses, and some without those big red double-decker delights. Clever humans among us have taken on the task of labeling these images, painstakingly marking which ones contain buses and which ones don't. Hell, even the more mediocre humans can teach the AI in this area. This is all free labor while we are trying to sign up for something online. With millions of these bus-filled and busless photos at its digital fingertips, machine learning does its magic. It tirelessly sifts through the data, searching for patterns, deciphering the subtle clues that make something a bus, without having to explicitly jot down a rulebook on the subject. Machine learning is all around us, hiding in plain sight like a stealthy ninja. You've got recommendation systems like Netflix and Spotify, analyzing your viewing and listening habits to serve up personalized suggestions. It's like having a movie aficionado friend who knows your taste better than you know yourself. Ah, I see you enjoyed Stranger Things. Might I recommend Dark as your next binge? And let's not forget about self-driving cars. This is not as narrow as a recommendation system, but it is still narrow. They can spot pedestrians, navigate traffic, and even parallel park better than most humans. So if you're ever feeling inadequate about your parking skills, just remember that machines have got it covered. Is this robotics, or is it narrow AI? Is it both? I told you this is all rather fuzzy. Now, machine learning isn't just about teaching computers to mimic human intelligence. It can also uncover patterns and make predictions that even the keenest detective would envy. Take the realm of finance, for example. Hedge funds and investment firms use machine learning algorithms to analyze mountains of data, looking for those hidden gems of profitable investments. It's like Sherlock Holmes with a supercomputer, deducing stock market moves with uncanny accuracy. But let's not get too carried away with the success stories. Machine learning, despite its brilliance, isn't infallible. Take, for instance, the tale of its misguided attempt at diagnosing cancerous cells in photos. In its noble pursuit to separate the malignant from the innocent, it stumbled upon a peculiar correlation. You see, in the training set, those sneaky scientists had only inserted a ruler next to suspicious growths to measure their size. And what did our well-intentioned machine learning system deduce? If it spotted a ruler, it jumped to the conclusion that cancer was lurking nearby. Oops, bias detection failure, my friends. It's a stark reminder that we must be ever vigilant when it comes to biases in our training sets. Machine learning, for all its prowess, can't differentiate between useful patterns and coincidental quirks without proper guidance. We must strive to provide it with fair and balanced data, free from unintended influences, to prevent such mishaps. Some are amusing, but others can perpetuate biases of the past. Next up is deep learning. Now, you just heard the term machine learning thrown around, but deep learning takes things to a whole new level. Simply put, deep learning is a subset of machine learning that involves training artificial neural networks to learn and make decisions based on large amounts of data. These neural networks consist of multiple layers of interconnected nodes, and the learning process involves adjusting the weights and biases of these connections to improve the accuracy of predictions. Now, you might be wondering how deep learning differs from regular machine learning. Well, while traditional machine learning algorithms can be effective at solving specific problems, they often require a human expert to identify the right features or inputs to use in the model. A human basically needs to say, the length of vehicle is important when identifying a bus. Deep learning, on the other hand, is more flexible and can automatically learn to identify relevant features from raw data, making it well suited for complex tasks like image recognition, natural language processing, and even playing games. In fact, one of the most popular examples of deep learning in pop culture is the AlphaGo program developed by Google's DeepMind. This program famously defeated world champion Go player Lee Sedol in a best-of-5 series in 2016, showcasing the power of deep learning for mastering complex games. You see, deep learning algorithms, with their complex neural networks and countless interconnected layers, can indeed be considered black boxes to some extent. They have the uncanny ability to learn and make decisions based on vast amounts of data, but the inner workings of how they arrive at those decisions can be somewhat elusive. Unlike traditional rule-based systems, where the reasoning and decision-making process can be explicitly explained, deep learning algorithms rely on intricate patterns and representations learned from data. This can make it challenging to understand exactly how and why a particular decision or prediction is made. In simpler terms, it's like trying to decipher the thought process of an enigmatic detective who solves a crime but refuses to reveal their reasoning. You're left with the outcome, but the path taken to reach that outcome remains shrouded in mystery. This black box nature of deep learning algorithms has raised concerns regarding transparency and accountability. When these algorithms are used in critical applications like healthcare, finance, or autonomous vehicles, it becomes crucial to ensure that their decisions can be explained and justified. After all, we wouldn't want a self-driving car to make a split-second decision without us understanding why it chose a particular course of action. Efforts are underway to tackle this black box problem. Researchers are exploring methods to interpret and visualize the internal workings of deep learning models, providing insights into the features and patterns they learn from data. Techniques such as attention mechanisms and model visualization tools are being developed to shed light on the decision-making process and increase transparency. One such approach is the development of explainable artificial intelligence (XAI) techniques. These methods strive to provide interpretable explanations for deep learning model outputs, making their decision-making process more transparent. Techniques like attention mechanisms, saliency maps, and gradient-based attribution methods offer glimpses into the features and patterns that influence a model's predictions. Another frontier in enhancing transparency lies in the field of model introspection. Researchers have devised methods to probe deep learning models, investigating their inner workings and understanding their limitations. Techniques such as sensitivity analysis, uncertainty estimation, and sensitivity to adversarial attacks enable researchers to assess a model's robustness and uncover potential biases or weaknesses. So while deep learning algorithms may have a tendency to reside in the realm of the unknown, efforts are being made to crack open that black box and shed light on their inner workings. After all, a little transparency goes a long way in building trust and understanding in the world of AI. Time now to talk about talking. Natural language processing. At its core, NLP is all about enabling machines to understand and process human language, whether that's written text or spoken speech. This involves a range of techniques and approaches, from parsing and analyzing the structure of language to identifying and extracting meaning from text. One popular application of NLP is machine translation, which involves automatically translating written or spoken language from one language to another. Other common applications include sentiment analysis, which involves automatically identifying the emotional tone of text, and chatbots, which use NLP to understand and respond to natural language queries from users. So how does NLP differ from other areas of AI, like machine learning and deep learning? Well, while NLP does often rely on machine learning techniques to train models on language data, it also involves a range of other approaches, including rule-based systems and probabilistic models. And because language is such a complex and nuanced domain, NLP also requires a deep understanding of linguistic and semantic structures, which sets it apart from other areas of AI. In popular culture, we see NLP applications in a variety of places, from virtual assistants like Siri and Alexa to predictive text algorithms on our smartphones, and of course large language models like ChatGPT. And with the increasing amount of language data available online, NLP is becoming more important than ever for everything from sentiment analysis in social media to automated content creation. Visual data is very dense and hard to interpret, and that is what computer vision is for. Computer vision is the field of AI that enables machines to analyze and understand images and videos. It involves tasks like image recognition, object detection, image segmentation, and even video analysis. The goal is to develop algorithms and models that can extract meaningful information from visual data, much like our own visual cortex does. Now you might be wondering how computer vision sets itself apart from other areas of AI, such as deep learning or machine learning. Well, computer vision often utilizes these techniques as its backbone. Deep learning, in particular, has been revolutionary in the field, empowering models to learn complex patterns and features directly from images or videos. Computer vision finds its way into many aspects of our lives, even in pop culture. You've likely seen it in action when your smartphone automatically recognizes faces in your photos or when you unlock your device using facial recognition. The applications of computer vision are far-reaching. From autonomous vehicles navigating the streets to quality control in manufacturing, from medical imaging analysis to augmented reality experiences, computer vision enhances our perception and understanding of the visual world. But of course, challenges persist. Teaching machines to truly comprehend images and videos at the same level as humans is an ongoing endeavor. However, remarkable strides have been made, and computer vision continues to astound us with its advancements. Robotics is the field that brings together the design, development, and deployment of machines known as robots. These mechanical wonders are equipped with AI capabilities, allowing them to interact with their surroundings and perform tasks autonomously or with minimal human intervention. From assembly line assistants to exploratory rovers on distant planets, robots have captured our imaginations and revolutionized various industries. Now you may wonder how robotics fits into the grand scheme of AI. Well, robotics often incorporates AI techniques like machine learning, computer vision, and natural language processing to enable robots to learn, adapt, and make intelligent decisions based on their environment. The fusion of AI and robotics results in machines that can perceive, reason, and act in the physical world, mimicking or even surpassing human capabilities in specific domains. In popular culture, we see a myriad of references to robots, from the adorable and helpful BB-8 in Star Wars to the self-aware and philosophical AI character Ava in the movie Ex Machina. If these are not the robots you are looking for, maybe Boston Dynamics' Big Dog is. These representations provide glimpses into the potential of robotics and the ethical dilemmas that arise when machines approach human-like behavior. The applications of robotics are vast and ever-expanding, from robotic surgery in hospitals to autonomous drones surveying landscapes, from collaborative robots, or cobots, working side by side with humans on factory floors, to companion robots providing support and companionship to the elderly. Robots are transforming industries and our daily lives. It is interesting to think that there is a planet in our very own solar system that is solely populated by robots.
Ladies and gentlemen, we are approaching Mars' lower orbit.
Yet, robotics also faces challenges. Ensuring safety, addressing ethical considerations, and developing robots that can adapt to diverse environments are ongoing endeavors. But as technology advances and researchers push the boundaries of what robots can do, the possibilities seem limitless. In the primordial soup theory, it is believed that life on Earth emerged from a concoction of organic molecules and chemical reactions, gradually forming more complex structures until eventually giving rise to the first living organisms. Similarly, we can envision narrow AI as the building blocks of AGI, coming together and evolving to create a new form of artificial intelligence. Just as the primordial soup provided the necessary ingredients for life to emerge, narrow AI systems provide the foundation for AGI to take shape. Each narrow AI system excels in its specific domain, mastering tasks like image recognition, speech synthesis, or natural language understanding. They are the specialized components that, when combined, contribute to the emergence of a more versatile and powerful AI entity. Just as the organic molecules in the primordial soup interacted and combined to create more complex structures, narrow AI systems can collaborate and integrate their capabilities, leading to the development of AGI. This convergence could involve sharing knowledge, learning from each other, and establishing connections between different domains of expertise. However, it's important to note that the transition from narrow AI to AGI is not a straightforward progression. Just as the leap from organic molecules to living organisms required specific conditions and complex evolutionary processes, the development of AGI demands significant advancements in AI research, algorithms, and hardware. Moreover, while the primordial soup theory suggests a somewhat spontaneous emergence of life, the journey towards AGI is driven by human ingenuity, possibly with the help of today's early AI. This is a deliberate engineering effort. It is the result of countless hours of research, development, and experimentation by scientists and engineers who push the boundaries of AI capabilities. So, while the analogy between the primordial soup and the convergence of narrow AI towards AGI provides a whimsical perspective, it's important to recognize the deliberate human agency involved in the creation of AGI. It is a journey fueled by human intelligence and innovation, bringing us closer to the realization of a new form of artificial intelligence that challenges the boundaries of human potential. And who knows, perhaps in the not-too-distant future, we'll witness the emergence of AGI. A transformative entity that surpasses the sum of its narrow AI predecessors, much like life emerged from the primordial soup. Until this Cambrian AI explosion, we will keep going one system at a time. And there you have it, dear listeners, a whirlwind tour through the captivating world of artificial intelligence. We've explored the elusive unicorn of AGI, the virtuosos of narrow AI, the detective skills of machine learning, the flexibility of deep learning, the linguistic prowess of natural language processing, the visual acuity of computer vision, and the physical embodiment of intelligence in robotics. Until next time, keep calm and carry on.